Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Our today lecture is lecture number 38, unit 16, physics of solids, and I'm your teacher, Muhammad Ikram. So I welcome you all here. Our today topics are the most important topics, which are superconductors, theory of magnetism, modern view about magnetism, and hysteresis loop. So let us start with our topic, the superconductors. Now, what are the superconductors? The superconductors are the kind of conductors which offer no resistance to the flow of which offer no resistance which offer no resistance to the flow of electric current to the flow of electric to the flow of electric current, which offer no resistance to the flow of electric current. So what does this really means? That here what we will observe is the no energy loss, no energy loss, either in the form of what? No energy loss, whether heat, sound, light, or whatsoever. Okay, so these kind of substances are called the superconductors, and I would like to tell you the history of the superconductor, a little bit history, that what leads to the superconductivity. It is most probably the early 20th century, where the scientists were studying the effect of conductivity when at nearly minus 273 degrees centigrade. Yeah, that is the effect of temperature. The effect, which temperature? Low. The effect of temperature. The effect of temperature, that temperature is low temperature, on the conductivity of certain material, on the conductivity of some material, of some material, right? That is nearly in the region of this temperature is in the region of minus, that is nearly minus 273 degrees centigrade, nearly absolute temperature. And here the strange phenomena occurs, which I am going to explain. Now, the classical mechanics or the classical electromagnetism failed to explain the phenomena of superconductivity. Right in the beginning, I want to tell you that once when you apply the external electric field across the ends of the superconductor, and once the current is established inside such material, so when you disconnect the potential difference source, the current will not fall to zero. The current will still remain the same. And here is the best example, as you see the magnetic leviation. So here you see the superconductor, and that is, you see here a permanent magnet, and you see that the magnet float. in the air, right, without any support. As you see right here, the gravity is being balanced by this strong magnetic repulsive force, and it float in the air. Now, what is the reason here? One simple thing which I told to you, and here I would like to explain to you. It is just in, if you see in the Newtonian mechanics, that F is equal to what? F is equal to ma. And there I told you that we need force to initiate the motion, but we don't need force to maintain the motion. So you may have seen that F might be zero somewhere, but the motion may not be equal to zero. The body velocity or speed may not necessarily to be zero. Okay, the body may have uniform motion. In the same regard, the Newton law of the electricity and magnetism is V equals R into I. Here R play the same role as mass. Here mass resists acceleration. Here resistance resist current. So in the superconductor, for superconductors, when V becomes zero, once the current is established, I will not be equal to zero. Why? Because in superconductors, we have what? We have R equals zero. There is no resistance in the superconductor, right? So that is one of the important beginning for explaining the phenomena of the superconductivity. Now, how the superconductivity can be achieved? As I told you that superconductors allow the flow of current with zero resistance, allow the flow of current, allow the flow of current with zero resistance, with zero resistance. What it does, it allow the flow of current with zero resistance. The now when this happens at temperature called, this all happens at temperature called critical temperature. Critical temperature. At a temperature called the critical temperature Tc. This happens at a temperature called the critical temperature Tc. Right? At this temperature, that is a temperature which is very low temperature. So this cannot be achieved without the consumption of any energy. So when the material and there is this temperature, it is at nearly, there is, for example, at around 4.2 Kelvin, which is extremely small temperature. The material chosen for this experiment material are substances, for example, mercury, right? Or you may say lead can also be there. So the critical temperature, it is different for different substances, depends on the nature of that substance. So when they go into very cold state, right, then the material just all of sudden at the critical temperature, their resistivity disappear and they become ideal conductor for the current. And we say that the material, that this is only possible, superconductivity is possible when the material or the substance when the substance is in its low energy state. Low energy state. Why? Because the temperature is lower. So lower the temperature, the lower the energy become. Now there is no there is no explanation in the classical mechanics for this sort of phenomena. So here we can explain the phenomena of superconductivity on the basis of its quantum mechanical nature. Yeah, quantum physics can explain this quantum nature of the material, right? And as there is no proper explanation to superconductivity in your book, but I would like to tell you that quantum mechanically, when the material goes into the low energy states, then they behave differently. Electrons behave differently. All the electrons behave differently when in the very low energy state, in the low energy state. And rather all the electron move in pairs, right? Not just like the solo electron does in the ordinary metallic conductors, right? Where it can face many kind of resistance collision from its own species like other electrons from atoms, and they can be slowed down and the resistance can be greater. Just like when in a busy traffic, when a car may have more and more resistance, but once when you are on the highway or on the motorway on a fast lane speed, right? So if you have all the cars in a pairs on the fast lane car, they can move without any resistance. So the quantum mechanically in the low energy states, all the electrons in pair move in one direction without any resistance. Now, so here you see, look, here you see that when you see that when the temperature is decreased, as you see decrease in the temperature for the non-superconductors, what you see here, that look at this point, that even when the temperature is nearly absolute Kelvin, right, you see that even then the resistance does not falls to zero. But for super material, for some conductors, here what you see, that as the temperature decreases at certain temperature called the critical temperature, the conductivity falls to zero all of sudden. Here you see it falls to zero all of sudden, and the substance becomes superconductor. So as I told you about the material like mercury, lead, and then in the 1986 a race has been started to produce superconductivity at relatively higher temperature. The engineer and the scientists are trying to obtain superconductivity at relatively room temperature until now, which is almost impossible, right? And there is reason for the impossibility. Why? Because that if you increase the temperature, or if you want to achieve this at relatively higher temperature like a room temperature, then the quantum mechanical nature get disturbed and they moves from bad conductivity, from superconductivity towards the bad conductivity, right? and this is why it is until now impossible for the room temperature. But however, there are certain material like compounds, ceramic compounds like the so that is those compounds, they can be changed to superconductivity from the critical temperature from 35 Kelvin to 125 Kelvin. So they are relatively higher temperature superconductors. This is what for which the scientists are looking. The example may include the compound of thallium, calcium, barium, copper, and oxygen together. So they may be superconductor at relatively higher temperature. The applications of the superconductivity, it has vast applications, vast number of applications. For example, in the MRI, magnetic resonance imaging, right, to generate a large magnetic field so that the doctor can see inside the human body invisively without being open surgery. So superconductors are used to achieve high magnetic field, right? Similarly, in the magnetic leviated trains, right, to reduce resistance, magnetic leviated trains, right? And most importantly, in the, you can say that in modern this era, like for example, in the cellular phone technology. In the cellular phone technology, for example, in some electronic filters, superconductor can be used. And now, for example, I would like to tell you, maybe in future we may have our computers or tablets based on a kind of technology which use superconductors, and you may operate your computers in the Sahara desert where the highest recorded temperature is 58 degrees centigrade, right? So this is these are the applications of the superconductors, right? Now you see that look, let us the our new topic is the theory of magnetism. Theory of magnetism. The theory of magnetism, that how substances behave when there is a magnetic field, yeah, how they respond to an external magnetic field, right? So the theory of magnetism, they describes Artill's few important points. For example, the particle of magnetic substances points in all direction normally under the influence of no external fields. The particles, by particles I mean molecules are atoms. Molecules are atoms of the magnetic substances, of the magnetic substances, of the magnetic substances points in all direction. Points in all direction. Points in all direction. That is what I can say, that they are randomly oriented. They are randomly oriented. They points in all direction means randomly oriented. And they acts as a tiny magnet, or they acts as a tiny magnets with random orientation. Here you see, look, each atoms here, look, see here, look at the orientation. This is North Pole and this is South Pole, and you see they are all randomly oriented. So under the influence of no external field, they cancel out the effect of each other. Cancel out the effect of each other, and resulting zero magnetic field, या net zero magnetic field, right? So that is the what we can say, that they have free poles near the ends, right? That look, you just see that there is no magnetic field here. The magnetic field density is zero. So they do not behave as a magnet. Right now, under the influence of external magnetic field, under the influence of external magnetic field, the substance behave as a magnet, right? And what we say, that magnetization of the substance occur. Magnetization, the substance behave as a magnet. For example, here, if you bring a permanent magnet near the a permanent magnet, look, for example, you see, look, for example, if I bring a permanent magnet, like look, for example, if this is I have a permanent magnet with this is the North Pole, right? And here we have the South Pole. So now look what happens. The external, you just see that all the particle are the molecules which are supposed to be a tiny magnet. They align themselves in one direction, and they just behave as a magnet, as you see, with its south pole this and with its north pole this. So in the magnetic substances, in the presence of a permanent magnet, behave as a magnet. So that is the theory of magnetism, right? And this is known as magnetization of the magnetic